Math.
Hi everyone, my name is Kargwa and Treasure.
My name is Anne Mustafa.
I'm called Mabe Junior Humphrey.
And we are presenting our project named the Multimodal Acoustic Electrical Feature Extraction Framework for Machine Learning-Based Partial Discharge Classification. With this project, we aim to detect class of partial discharge, classify it, and also localize where the partial discharge comes from in high voltage equipment. Our group code is as shown. In this presentation, we're going to cover our problem statement, the research questions we looked at, our system architecture, the dataset description, our results from the exploratory data analysis, any conclusions, that limitations we faced, and a counteraction plan. Partial discharge is an electric spark that occurs within the insulation of high voltage equipment that leads to the degradation of that insulation. Repeated electric sparks can lead to the degradation of insulation, the equipment failing, and can even lead to fires due to short circuits that can be caused by the insulation failure. Eye detection is critical in order to ensure predictive maintenance of such expensive electrical equipment. These high voltage assets we aim to protect include transformers, generators, and switch gears. So high voltage power equipment are especially vulnerable to partial discharge, which can lead to the breakdown of the insulation. So this partial discharge can in turn lead to significant financial and safety risks, which can lead to high financial losses of the companies involved. So the current maintenance practices that we see are mainly reactive, but what we aim to do is to produce a proactive solution. So the computational problem we look at is that partial discharge charge signals are high frequency and they're very noisy, and they are affected by broadband interference, which means that you cannot hear them. They are hard to hear unless they're at the later stages, and they are feature redundant and they're very highly correlated. So we aim to solve it by extracting discriminative time domain and frequency domain features, differentiating between corona, internal, and surface discharge types, and also determining the source of the partial discharge, that is the location of partial discharge in huge high voltage equipment. And we aim to enable predictive maintenance through the automated partial discharge classification. So the questions that we looked at we aim to verify the data how complete our data is, and the different characteristics of the waveforms, to extract any features, and to also evaluate clustering and channel correlations, especially in the acoustic dataset. With the electric dataset, we also aim to see if the dataset is consistent. We also aim to extract the different features, especially the time domain pulse behavior, and also analyze these patterns, and also extract and compare any features for classification. So in our system architecture, we have a data input layer, whereby we have sensors for both electric signals and acoustic signals. So with this information, it's fed into the neural layer, which has our machine learning models that carry out the classification and localization. We have the pulse detection that we're able to pick up on the pulses, especially of the electric signals. The feature extraction layer, we aim to extract the different features, and the probabilistic matching, we aim to calculate the probabilities of each type of partial discharge happening. So this is fed into a causal layer, which is informed by physics, whereby in the causal layer we have the time of arrival, which helps in localization and any physics validation. And the symbolic layer, we apply the rule-based knowledge based on the physics domain, whereby we see that if a certain wave has a particular shape, we can be able to say that it belongs to surface partial discharge or corona surface partial discharge. So in the agentic layer, we aim to explain the results that we get, and in the final output, we aim to output the partial discharge types, the confidence, and the localization of where the partial discharge has taken place. So in our dataset description, we had two datasets. We had the acoustic dataset, which was recorded from a 32 channel MEMS microphone. We're sampling rate of 96 kilohertz, whereby each recording was for 50 seconds. And we have acoustic signal categories of partial discharge, the chaps, and white Gaussian noise. And then for the electrical partial discharge, we had 250 controlled laboratory partial discharge acquisitions using a high frequency current transformer. This is an equipment for capturing electrical signals. And with this, we're able to see that the dataset contained 4 discharge types, which was the corona surface, the internal in solid insulation, and the internal in liquid insulation. And with that data analysis results, we saw that the acoustic analysis of corona surface and internal partial discharge, and we're able to get these features such as the peak amplitude, the zero crossing rate, and spectral centroid in order to capture the intensity and frequency characteristics. And also with the electrical partial discharge dataset, it consisted of the 32 millisecond signals that were sampled at 325 with no duplicates, and we're able to analyze and get these features and determine the pulse behavior and the different features. So to come to the analysis of the acoustic dataset, we're able to see that we had over 8,000 files, and with our spectrograms, we're able to see the frequency range of both the chaps, the white Gaussian noise, and the partial discharge to see where the frequency lies. And then with that time and amplitude graphs, we're able to see the amplitude of each of these waves, and we're able to determine the shape of partial discharge, white Gaussian noise, and also the chaps, what they look like. So these are the shapes of the different signals in our data set that we're able to extract. And from our feature correlation mix, we saw that the MCC, which represents the fingerprint of the sound, we saw that there were a high correlation between different types of MCCs, which means that we shall have to drop some of those features. And there was also a high correlation between the RMS and energy, since the RMS is the root mean square of the energy, you shall have to drop one of them. And from the arrays, from these images, we're able to see where the signal is. We're able to see that the signal is captured in different parts of the signal of the different parts of the 32 channels, whereby some of the signal is captured at the edges and the signal is also captured in the middle. And then from the frequency reports, we're able to see that the partial discharge has a frequency ranging from 2,000 Hz to 15 to 16,000 Hz. White Gaussian noise has a signal ranging from 4,000 to 19,000 Hz, and then you have the chaps having a signal that has ranges from 1,000 to 10,000 chaps. From these violin graphs, we're able to see that the centroid feature is a feature that best differentiates between the partial discharge, the white noise, and the chaps. Maybe the other feature you can talk about that has a higher differentiating power is the roll-off that we see here. My colleague Humphrey will take over with the further analysis of the acoustics dataset.
Thank you so much, Treasure. Furthermore, we did EDA on the acoustic dataset only, and from that analysis, we were able to visualize a number of things, as you can see on this slide. As I will take you through some of the visualizations that we got when we did the EDA on the acoustics only dataset. The first visualization that you see is a spectrogram. The spectrogram shows us the frequency content of an acoustic partial discharge recording over time. The x-axis is time in seconds, and then the y-axis is a count. Yeah. Sorry, the y-axis is the frequency. Sorry, it's a frequency. It goes up to 10,000 Hz. So the color intensity represents strength. Now purple is weak, and then red is strong. So you can notice the vertical striping patterns. Those are periodic bursts of acoustic energy from the partial discharge event. Now, this These bursts occur at regular intervals, which physically characterizes PD activity. Now, the spectrogram is our first clue that there are hidden structures in raw audio. Now, the different PD types have different frequency signatures, and this visual tells us acoustic features allow us to discriminate the different types of PD. Now, second visualization is a signal to noise ratio histogram. The histogram shows the signal to noise ratio across all the files in a dataset, uh, specifically a random sample for visualization. As you can see, the signal to noise ratio measures how strong the PD signal is compared to the background noise. The x-axis goes from -5 to 0 decibels, and then the y-axis is a count of the different files that we actually have. So you can see you can notice the extreme what left skew. As you can see, almost all the files cluster between -3 and -4 decibels. Now this tells us that our recordings are actually very noisy. Now most acoustic files have a signal to noise ratio of around 10 decibels. Now since ours lies around -3 decibels, this means that the noise is almost as loud as the signal that we have uh, in our audio files. The third representation is also a histogram, but this histogram is more of a mean amplitude distribution one. It shows us how loud on average each file is. The x-axis is the mean amplitude, and then the y-axis is a count. And the distribution is heavily skewed, like towards the right with a sharp peak around 0.0008. Uh, this tells us that there's a huge variation in signal strength across the different recordings. And then the visualization down, it's just a sample PD segment. Now, we know that our each audio file is 50 seconds long. Yeah. Here we're trying to show that when you segment one file, as you can see, the background color, I think it's kind of red. Now, the background color uh, it shows us the background noise. And then the different spikes in bursts, those are the different bursts in PD activity. Now that's just trying to show us the one audio file and how it runs over the 50 seconds. And then the last visualization on this slide is the waveform overlays. Now we know that our sensors are organized as 32 channels each location. Now here we overlay all the 32 channels from one location at the same time. Now each channel is a different color. The x-axis is obviously time. Uh, and the y-axis is the amplitude. You can see that each channel shows similar burst patterns. Now the PD even generates acoustic waves that propagate to all the 32 sensors. But then you notice the amplitude varies by channel. Some channels are louder than others, and this is expected because, of course, closer channels record stronger signals compared to the ones that are farther out. Please move to the next slide. Uh, this slide, the topmost visualization, that's the represents the the MFCC mean. MFCC stands for the male frequency substrate coefficients. Now, this is how actually humans and speech recognition systems understand sound. Instead of a raw frequency, MFCC's map frequency is onto the mel scale, which matches how the human ear actually perceives pitch. So we compute the maybe 13 different MFCCs for each audio segment and then average them. And the histograms show us all what we're trying to find out. These are different features we're trying to extract from our different what audio files. So we're extracting the centroid, the ZRC, the RMS, and then the roll-off. Those are all features that we're trying to extract to try and talk about our different talk about the PD that exists actually in our different audio files. And then bottom we have the bottom we have the RMS by channel. Now this is a box plot. This box plot shows the root mean square energy for each of the 32 channels across all the the segments in the files. Now every box represents a channel. The center line is like the median, the root mean square, and then the box height shows the spread. Now you notice that the channels have similar medians. They are all uh, they are all kind of the same, but the key observation is in the variation. Yeah, some channels, especially the mid-range channels, have slightly higher medians. This is consistent with sensor placement. Some channels are naturally louder due to proximity or sensitivity. Now, when you train the model, we normalize the channels to account for this, treating each channel fairly rather than letting a louder channel dominate other features. And the last visualization is a location now versus channel uh, representation. Uh, Now here you can see on the x-axis, we have the channel numbers from 0 to 30, and then the y-axis is also channel, but the color represents the estimated lag that exists in milliseconds. Now the diagonal uh, is always 0. Uh, However, it's always 0 when you compare a channel to itself. But off diagonal, blue means that the burst arrived first at the x-axis channel. Yellow orange means that it arrived first at the y-axis channel. Now, the complex pattern of colors tells us that the PD source is not at the center. Now, if it were, all the channels will actually receive the burst simultaneously. Now, this partial information which channels light up first, encode the direction and then the distance in the PD event gives us a geometric discrimination beyond which beyond the different acoustic features. I think that describes slightly this describes the EDA that we did on the acoustic only data set. Next, I'll request my group mate Ayan to take over the next slides. Thank you.
Okay, next slide. Okay, thank you. I'm going to start with the time domain analysis. Those are the first three graphs at the top. So I'm going to first talk about for the corona discharge, the signal shows many small repetitive sparks. These sparks occur frequently and follow a fairly consistent pattern. This indicates that the corona discharge produces continuous but low energy events, typically happening at a localized point, such as the sharp edges. Whereas when we go to the middle one, which is for the internal discharge, the the signal looks very dense and noisy, unlike the corona, whereby we cannot clearly distinguish individual sparks. So instead, the signal appears more continuous and random. This reflects the fact that internal discharge occurs inside insulation, where the activity is more distributed and less structured. And then when you look at the surface discharge, which is at our most right-hand side, the signal is mostly flat with occasional large sparks. These sparks are irregular, much stronger but they're much stronger compared to the corona discharge. This shows that the surface discharge happens less frequently, but when it does occur, it releases high energy bursts along the surface of the installation. Then I'm going to go to the spectrum analysis, which is the lower three, talking about the internal, the corona, and the surface. For the internal, which is at our most left-hand side at the bottom, uh, the spectrum shows a stable horizontal band which runs within the same frequency, meaning the signal energy is concentrated in a narrow frequency range and remains consistent over time. This reflects a repetitive nature. For the internal, we observe multiple horizontal bands, which are like three of them, but within different frequencies. This tells us that the signal contains multiple frequency components, making it more complex or hard and less predictable. And then when we look at the surface, the spectrogram for the surface discharge, the spectrogram shows vertical bursts. These represent short, they represent short events that occur at specific times rather than continuously. Next slide, please, Treasure. Then for this area, I'm going to first start with the statistical features, which is at the top right-hand side, that box that talks about the mean, the STD, the max, and all that. So here, these are the statistical features from the signals. So the most important features here is the kurtosis, which measures the shape or or the sparkiness, if that English is correct, of a signal. Then when you look at when you look at the surface discharge, the kurtosis is extremely high, whereby it's 347, which confirms that the signal contains very sharp and very rare sparks because due to its skew. Skew tells us how rare the sparks are. Then when you look at the coronal discharge, the kurtosis is moderate. It's around 74, which means it has sparks, but they are more frequent and less extreme. Then when you look at the internal discharge, the kurtosis is very low. It's around 4, which indicates a more normal noise-like signal without strong sparks. So skewness shows us that the surface discharge has strong asymmetry due to the large sparks, while the internal discharge remains close to zero due to the high noise. Then when you look at the feature correlation at our top left, this shows us that the correlation heat map, it shows us that the RMS and the standard deviation are highly correlated, meaning they capture similar information, so therefore we'll have to remove one of them they're both talking about the signal energy. Then when you look at the maximum value and the kurtosis, they're also strongly correlated since both depend on extreme sparks. So this tells us that some features are redundant and we select small set of meaningful features for training our model. Then when you look at the bottom side, those are the frequency spectrum analysis on the second row, whereby here for the coronal discharge, we observe a dominant frequency peak, meaning most of the signal energy is concentrated in a specific frequency band. For the internal, the spectrum shows us multiple peaks across different frequencies, indicating more complex signal structure. Whereas for the surface, when you look at it very carefully, um, when you look at we see both a strong spark and a broad spread of the frequencies, reflecting a combination of burst-like and noisy behavior from both. So, next slide, Treasure, please. Treasure? Yeah, thank you. Uh, from our conclusions and our limitations, the acoustic and the electrical PD datasets show distinguishable signal characteristics along the corona, surface, and the internal discharges. Then for the time domain and the frequency domain that were highlighted from all the above features, there were variations in energy, in amplitude, and the spectral distribution. where the acoustic features demonstrate strong class separability compared to the electrical features alone, as previously described by my colleague. Then let me just jump into the limitations due to that limited time. So here, the data sets were collected under a controlled laboratory condition, as also my colleague said before, which may not fully represent real-world industry environments. So maybe in the future, we will try to consider the outside field. Then for the electrical signals have extremely high sampling rate, whereby their sampling was actually very high, leading to thousands, whereby since the data sets they lead to large data volumes and computational complexity. Then finally, limited discharge categories may restrict model generalization. Next slide, please. Okay, so for our next steps, whereby most of this have already been done, we have done the EDA part, then we also did the feature engineering, then we integrated, whereby we built multi-models from both the acoustics and the electrical datasets. Then we also implemented localization algorithms that could help us find the area within which the discharge is happening due to the models that we also built. Then we also did test robustness under real. We're going to do that one. We haven't yet done it. Sorry, that step. Under real conditions. That's when we deploy it finally. Next page, please. Next. Then those are our acknowledgements. Thank you very much for listening. Treasure.
Thank you so much for staying along to listen to our presentation. Have a nice day.